Assalamualaikum warahmatullahi wabarakatuh. So today we are going to do a description about classification of lever and moment of force. Firstly, we are going to talk about classification of lever. Human has used levers for thousands of years to make their work easier, such as wheelbarrow, a pair of scissors, hammer, crowbar, tongue, and lemon squeezer. A lever is a rigid rod capable of rotating about a fixed point called fulcrum. Here is a schematic representation of a lever. Levers are classified into three kinds on the basis of the relative positions of effort, load, and fulcrum. To understand the meaning of the effort, load, and fulcrum, let us view the example of a boy moving a boulder using a crowbar. The force that applies on the crowbar is called the effort. The weight, in this case, the boulder that is being pushed is called the load. And the point at which the crowbar is pivoted is called the fulcrum. Now, let us understand the different types of levers based on the relative positions of the load, fulcrum, and the effort. In class 1 lever, the fulcrum is in between the load and the effort. A crowbar, a scissors, and a claw hammer are some of the examples of class 1 lever.
So, in class 2 lever, the load is between the force and fulcrum. So, the conclusion for the class 2 lever is the closer the load is to the fulcrum, the easier the load to lift. In a class 3 lever, the force is between the load and the fulcrum. Next, for example, broom. So, the upper part of the broom is called fulcrum. The middle part of the broom is called effort. And so, the conclusion for the class 2 lever is the closer the load is to the fulcrum, the easier the load to lift.
My topic will be moment of force. Think about a spanner losing a fixed net, or a child on a seesaw. All of the things are connected by something called moment. A moment is a turning force around a fixed pivot. The pivot is the net, or the middle of the seesaw. We can have one moment acting, like so, which results in a turning force. Or if something is balanced, or in equilibrium, like shown in this diagram below, the moments are equal and opposite. To be balanced, the lighter child needs to sit farther away from the pivot, and the heavier child needs to be closer. This is because size of a moment is determined by the force and distance. So the moments of force for both child will be the same and perfectly balanced on the seesaw. The moments are measured in Newton meters, which is Nm, because force because force is measured in Newton and meanwhile distance is measured in meters. Note that the distance must be the perpendicular distance from the pivot to force. We can also place formula into a formula triangle. Force equals to moments divided by distance. Distance equals to moments divided by force. And moments is force times distance. Here is an example question. The moment exerted is 12 Newton meter. What is the force? This question wants to know the force. The formula for force is moment divided by distance. In the question, it is stated that the moment is 12 Newton meter and the distance is stated as 2 meter. So the force equals to 6 Newton. This is all for moment of force. Thank you.
So I'm going to explain about how to solve moment and equilibrium force question. Okay, now look at the moment of force of the three spanner, which is the situation A is the spanner is easily to create a bigger moment of force, while the second one is harder and the situation C is the hardest. What can I conclude from here? When the perpendicular distance between direction of force, which is base, and the nut is much longer, the moment of force can be created bigger. Moving on to the next slide. Question 1. Calculate the moment if a force of 5.1 Newton meter is applied to a spanner that is 15 cm long. Question 2. What force might be applied to a 30 cm long spanner to generate a moment of 6 Newton meter? So move on to the solving part. So the first one is the force is 5 Newton, while the distance we have to change it to meter, which is 15 must be over 100 to gain the meter. So the moment of the force is 5 times with 0.5 to create 0.75 Newton meter. So this is the answer for the question 1. For the question 2, which is what force must be applied? What force must be applied to generate moment of 6 Newton meter? So moment, as we know how to calculate moment, force must be timed with distance. So if you want to calculate the force, you have to divide moment with distance, which is the moment equals to 6.0 Newton meter divided by 0.3 meter, which is 3 centimeter, that we change into meter. So you will get 20 Newton as a result. So this is the answer for the calculation of force that is generated to 6.0 Newton meter. So moving on to the balancing force equilibrium. So balancing force is usually called equilibrium. That is, the anti-clockwise side and the clockwise side must both have the same moment of force. So it has to be same to make it balance, either the distance or the weight. So let's moving on to the questions. For the simple calculation. Okay. Question 1. Suppose distance 1 is 2.5 meter, weight 1 equals to mass of 55 kilogram. Distance 2 equals to mass of 50 kilogram. It is balanced. Is it balanced? So let's moving on to the solution. Let's moving on. So here it is stated that the distance 2 is 3.0 meter. I forget to write it. So let's moving on to the solutions. So we have to calculate the moment of anti-clockwise first. The formula is distance times width, weight as we known. So 2.5 meter times weight, 10 times 55. Why 10 times 55? That we have to change kilogram into gram. So it will become 1,375 Newton meter. So moving on to the clockwise moment, which is we added the same formula, that is distance times width, weight. We gain 3.0 meter, and 10 times width 50 that we have to change kilogram into gram. So we will gain 1,500 Newton meter as a result for the clockwise moment. So let's have a look here that 1,375 is less than 1,500 Newton meter. So the ruler will turn to clockwise. Why? Because both of this is not balanced. So we are moving on to the complex calculation. Look at the questions. A beam is placed evenly on a pivot point fulcrum. On one side, a 10 Newton weight is placed 2 meter from the pivot point, and a 14 Newton weight a further 4 meter from the pivot point. How far from the pivot point must the center of gravity of an 8 Newton weight must be placed to perfectly balance the beam horizontally? So let's moving on to the solutions. So we have here that balance force is equals to both sides have the same moment, as I told you before. So we have to find the meter that can be applied, that can be multiplied by the Newton of 18 to make it balance with 260 Newton meter. How do I get it? I get it from the multiply, the combination, multiply and addition of the second clockwise. So this is the unknown that we have to gain, we have to see for, we have to search for. That is the distance. Unknown equals to distance. So the distance, when we try to find the distance, we have to divide the 260 Newton meter by 18 Newton. So we will get the result is 3.25 meter. So the 18 Newton must be placed left 3.2 meter away from the pivot point to make it balance. So that's all for me. Thank you.